Hi, in this video we will learn that one can compute the determinant of a square matrix by expanding along any row or column of that matrix. It's called cofactor expansion. So far what we know about the determinant of an n by n matrix is that while you do multiply entries of the first row to the corresponding cofactors. Yes, 1 entry to 1 cofactor, then add to 1 entry to 1 cofactor, and then continue this work until you get 1n entry to 1n cofactor. Other way of writing this would be that we are adding or sum of entries of the first row times corresponding cofactors. So you multiply each entry of the first row to the corresponding cofactor and add them. Well, there is a theorem or a fact which says that, well, you don't need to always to find the determinant by cofactor expansion along the first row. You can indeed do this thing. The terminal, I just write as a continuation of that equalities, sum of, you choose any row you like, entries of the ith row. So you multiply each entry by the corresponding cofactor. Depending which row you choose, that you will get different cofactors. You multiply each entry to the corresponding cofactor and add it. And indeed, this can be done in also different way. You can also do the cofactor expansion on the entry along a jth column. So it means that multiply entries of jth column to the corresponding cofactors and then add all of them. So this will be a cofactor expansion along row I, and this will be cofactor expansion along column J. You choose which row or which column you want to do this expansion along, and then the formula, the term guarantees that you will get the same number for the determinant. Okay, let's see this in an example. So the example is find the determinant of this 3 by 3 matrix 0, 2, 1, 1, 2, 3, 0, negative 1, 1 by cofactor expansion along. So first one you do it along row 2, and then do it again for column 1. Well, we are going to get the same number, but let's see here. So determinant of this guy along row 1, so row 2, this is what we have here. So Let me just write the formula along row 2 first. In this case will be, well, 1 2 1, sorry, along row 2. So I'll need to start with entries of row 2, which is 2 1 2 2 and 2 3. Multiply each entry by the corresponding cofactor. This guy 2 2 cofactor. Yes. And this guy here, a 2 3 times 2 3 cofactor. Okay. Then when you multiply those guys, then add them. Very nice. In this case, we have A21. So we are going to do everything along this row. So 1 times 2 1 cofactor. What is 2 1 cofactor? Well, you have to find minor 2 factor, 2 1 minor, and then multiply it by that sign. Remember that sign, we can get it by starting with positive for top left entry and then alternate as you go to the next entry. It doesn't matter in the row or in column. So I can do plus, minus, plus, minus. So here it will be minus determinant of 2 1 submatrix. Submatrix 2 1. You delete row 2 column 1, and then this is 2 1 negative 1 1 plus. So we are done with the first entry. The second entry of the row, the second entry of the row is this guy, and then it's 2, and then multiply. The sign is plus. Determinant of submatrix. In this case, the submatrix is going to be what? 0 1 0 1. And then the third one, the third entry is 3, multiply. The cofactor, the sign is negative, determinant of, okay, this guy here, 0 2, and then 0 negative 1. Okay, so we have that. Now you compute each piece and then add those ones. So this is 1 times negative 2 times 1 minus 1 times negative 1. Then plus 2, 0 times 1 minus 1 times 0. Plus 3 times negative 0 times negative 1. Plus 2 times 0. Okay, so this way we have 1 here. You see this down here is 2 plus 1 is 3. Then there's a negative 3. So this is negative 3 times 1 plus this guy here is 0. So 2 times 0 plus this guy inside is also 0, so 3 times 0. All together, we get negative 3. So we found the determinant by expanding along row 2, and it was negative 3. Well, how about if I do this thing by expanding along column 1? Okay, so let's try this one. I'll write down here determinant of this guy is 0 1 0 2 2 negative 1 1 3 1. And what is the determinant of this along column 1? Column 1 means that you choose entries of first column. These are entries of the first column. Add each one by the corresponding cofactor. So multiply each one by, yes, so this is cofactor, 2 1 cofactor. And this is 3 1 cofactor. When you're done with that, you add all these these products, yes? So in this case, what we have is A11 is 0. So then the cofactor. What is the cofactor 1, 1? We have a sign, -1 to the power 1 plus 1. That sign, you can choose it by start with the positive one on top left and then alternate as you move to the next entry. So the first one would be plus determinant of 2, 3, -1, 1 plus 2, 1 is, well, we are expanding along this row column. So this will be 1 times negative, the sign comes from there, determinant of, so this guy, yes. So this is 2, 1, and -1, 1. And then the last one, we are doing this piece here, and this is 0 times plus determinant of a 2 by 2 submatrix. So this is 2, 1, 2, 3. Well, you see here, when you have 0 entry, you multiply to that cofactor. Doesn't matter what is the cofactor. At the end, you'll get 0 plus 1 negative main entries of main diagonal minus of diagonal terms, you multiply them, plus, and this comes again the same, 0 times something is 0. I don't need to compute anything there. So this guy down there, this adds to these add to 3, there's the negative sign, and then that's -3. And as you can see, it doesn't matter expanding along which row or column. At least here we checked for column 1 and row 2 of this matrix. Doesn't matter. You choose any row, any column, and you expand along that row or a column. But as you can see, comparing these two expansion, in the second one, I did less computations comparing to the first one. Why was that? Why is that I needed less computation? I'm computing same determinant of same matrix, but when we expanded along column 1, we needed less computations compared when we expanded along column row 2. Well, this was because of the zeros in the column 1. So this is a remark that you need to keep in mind. A row or a column is a better choice for cofactor expansion along if it has, the row or column has more zeros. So if you have a matrix, you look first for a row or column which has more zeros, then use the cofactor expansion along that row or column. Why? Because you will need less computations. Okay, let's see this thing in practice. Example. Well, find determinant of a 4 by 4 matrix, 1, -1, -2, 4, and 0, 2, 1, 0, 2, 3, -1, 2, 0, 4, 0, 0. Well, you know that you can expand along any row or column. Okay, so here you can expand along row 1. It means that there is no 0 entry there. It means that you have to compute 4 determinants of 3 by 3 matrices. Okay, then add them. Okay, if you expand along row 2, you will get, oh, 2 zeros. There are 2 zeros, so I need 2 less determinant of 3 by 3 matrix only for these 2 entries here. Well, that's better. So definitely row 2 expansion along row 2 is better than expansion along row 1. And column 3, you see, it has column 4, it has 2 zeros. Well, that's also in the same level as the second row. But if you notice, the fourth row has 3 zeros. It means that if you expand along that, you will need to compute only one 3 by 3 determinant. Okay, so we are expanding cofactor expansion along row 4. Okay, what does that would give us? 0. So first, let me just write the entry was. So the first, the fourth row, so A for 1, A for 2, A for 3, and then A for 4. A for 1 multiplied to 4 1 cofactor. Added to A, A for 2 times to 4 2 cofactor. Added to 4 3 entry to 4 3 cofactor. And then added to 4 4 to 4 4 cofactor. Okay, here A for 4 or A for 1 is this guy, which is 0. So I don't need even to multiply this guy. Well, I do know what is that cofactor. At the end, it's going to be multiplied by 0. A for 2 is 4 times 4 2 cofactor. So what is 4 2 cofactor? Here I have I have to first tell you what is the sign. Start with plus here, minus, plus, minus. For 4 2 cofactor, we have the sign plus, then determinant of a 3 by 3 matrix. What is that 3 by 3 matrix? That's submatrix for 2. So it is 1 0 2 negative 2 4 1 0 negative 1 2. And then from there, plus, let me delete these ones. The next entry for 3 is 0. So I don't need to know what is the cofactor for 3. It will be 0. At the end, multiplied by 0, it will be 0. 4 entries again 0, and I don't need to compute those ones. So the result is that if I know what is a determinant of this 3 by 3 matrix, then I'm good to go. So I need to just find determinant of that guy. So for 3 by 3 now, I can choose any row or column. So we choose to do the along for this 3 by 3 along row 2. You see row 2 has 2 zeros, so that's better choice. So it will be 0 times here 2 1 cofactor plus 1 times 2 2 cofactor and 0 times 2 3 cofactor. Then add these guys. That's the determinant. Now the first guy is 0, doesn't matter what is 2 1 cofactor. The third one is 0. So here we need only to compute 1 2 1 cofactor, which is 2 cofactor. 2. Is it plus or minus? Well, I start with plus here, minus there, plus there. So it will be plus determinant of 1, 4, 2, 2. Yes. And what does that give me? So it's 4 times 1 times 1 times 2, 2 minus 2 times 4 times 2 times 4 is 8. And that's what we get, 4 times a negative 6, which when you multiply, you get a negative 24. And that is an example that shows, let me write here, negative 24, shows that how choosing a row with more zeros can help you to reduce the number of steps to compute the determinant of a matrix. This is especially important when you're dealing with 4 by 4, 5 by 5 matrices. Okay, so expansion along any row or column you like can be done. They will give you the same results. The better choice is the one that has more zeros, either the row or column. You choose one of them and then multiply entries of that row by the corresponding cofactors and add them.